provided a good overview of biological principles of swarms intelligence. Florio discussed swarm intelligence alongside evolutionary computation, artificial neural networks, and bio-robotics. Plum and Kozner addressed swarm intelligence-based algorithms. Swarm intelligence-based optimization algorithms are analyzed by Yang, and the links between swarm intelligence-based optimization algorithms and self-organization is examined by Yang and Razi, classifying existing multi-agent algorithms according to their underlying mathematical structure. Despite the large number of swarm algorithms, the step to industrial applications has not yet been mastered successfully. Yet, in our research work on real-world applications, we notice that sometimes industrial applications use the term swarm, but typically do not implement particular swarm algorithm. They're rather used parts of swarm algorithms and implement them using centralized control. We refer to such parts of swarm algorithms as basic swarm behavior in the following. The rest of this paper is organized as follows. In section 2, we propose a taxonomy of basic behaviors. In section 3, we show that these behaviors are applied by giving comprehensive overview of current swarm robotics research, platforms, projects, and the overview is implemented by a discussion that analyzes the current situation and explores open challenges in swarm robotic applications. Finally, in section 4, we conclude the paper. Basic swarm behaviors and swarm robotics. In most swarm algorithms, individuals perform according to local roles and overall behaviors emerging organically. The interplay of individuals in the swarm translated to swarm robotics domain. Individual robots exhibit a behavior that is based on the local role set, which can range from a simple reactive mapping between sensors, inputs, and actuators. Outputs to elaborate local algorithms. Typically, these behaviors incorporate interactions with physical worlds, including the environment and other robots. Each interaction consists of reading the implemented sensory data, processing this data, and driving the actuators accordingly. Since a sequence of interactions is defined as basic behavior that is repeatedly executed either indefinitely or until a desired state is reached, until a desired state is reached. In the following subsections, we classify a list of basic swarm behaviors which are adapted and expanded with additional swarm robotics, including collective localization, collective perception, organization, self-healing, and self-reproduction. The behaviors are explained from a high-level view, describing the task of individual robots and resulting global objective achieved by the swarm. We do not detail on the sensing and actuation part, which is specific to each robotic platform. Taxonomy. The taxonomy of a swarm behavior is given in Figure 1 and is based on the classification by Vanilla, which we extend by several categories. In the following, we first give an overview of the taxonomy, and then in detailed description of the actual behaviors, categorized in subsection 2.2. For these behaviors, we also give the original inspiration for the detailed descriptions of the existing categories. We kindly refer to the reader to Granville. Taxonomy of swarm behaviors adopted by Granville. The catalog of behaviors are newly added. The swarm behaviors. Spatial organization, where we have aggregation, pattern forming, self-assembly, object clustering, and assembling. Then we have navigation, collective exploration, coordinated motion, collective transport, collective localization, decision-making, consensus, task allocation, collective fault detection, collective perception, synchronization, group size regulation. Miscellaneous is the self-healing, self-reproduction, and human-swarm interaction. So what all of these categories of swarm behaviors are current, or do we have, or ideas that we have for implementing some of these into swarms?
I think spatial organization. We're doing this now. Like we're aggregating stuff, pattern formation, self assembly. Like we added we added some multimodality models in that like multimodality models like Idemficus by Hugging Face, Fufu by Adept. We've added these models in. I think that would be like a pretty good first step to achieve spatial organization. And yeah, I think spatial organization could be like pretty much swapped out with multimodality in our case. This is talking about more in a robotic case. So that's why they're talking about like aggregation, pattern formation, self assembly, object clustering. That means like organizing objects into like their bins or boxes. I definitely think spatial organization here means multimodality AI. We definitely need to work on multimodality AI if we want the robots or the agents of the swarm to understand the world around them, both in our framework and in the swarm's and robotic swarms. So then navigation, collective exploration, coordinated motion, collective transport, and collective localization. So collective exploration means kind of like imagine like you went camping the other week, right, Zach? That was collective exploration, basically. Um, Basically, they have to explore like possible solutions in a space. That's what that means, I think. Coordinated motion. So, like, you're obviously moving to the same objective. They have to be coordinated. They have to be moving towards the same objective. And as you witness, programming together and like we've worked on the same things a couple of times and we've created bugs on each other's code. So, like, coordinated motion is like a really big, important component of creating reliable swarms. I think that's definitely coordinated motion to the goal would be a better thing for that. So like how coordinated are we going to like how coordinated are we like taking actions together? I think that's what that means. Transport, that can mean like how is information being transported? Um, I think that like how is information being transported? Oh, through the vector database. Oh, okay. Um, it could also be like how the robots would actually transport objects with their hands with actuators. Do you know what an actuator is?
No.
Should look it up. Look up actuator
Yeah.
robot. So an actuator is like
I'm sure I will once I see the description. Go on.
So yeah, look up
actuator is a component of a machine that produces force, torque, or displacement, usually in a controlled way when electricity, pneumatic, or hydraulic input is supplied into a system.
So it's basically what makes the model activate, or like it's like the things that like look up actuator robots, and you'll see like they're what allows the robots to move, to act, to yeah go to images. Um, they're basically what allows the robot to interact. So like everything in the fingers, like when you see in those videos, the fingers that are moving, those are like all actuators. Um, you see that the Dynamixel AX12A robot actuator on the bottom right. It's basically what allows the robot to move its arm, to move its eyes, to move its legs. They're like the atoms of a robot, basically. So,
I see. Okay.
yeah.
And how would that apply to swarms then?
Well, to make robots, you need actuators. So you would basically a robot, one robot would be a swarm of actuators. So if the actuators are not positioned correctly, then it's not going to be effective. You know, that's the big thing. You understand? So
yeah.
They're basically like they're like a kind of like they just apply force in certain dimensions or a certain space and like yeah. Yeah, those are just robots. Yeah. So, where were we? Transports, localization. So that localization would be the vector database, or kind of like a shared embedding space. Decision making, consensus, task allocation. Consensus is important. That's like having like metrics. We need to be like logging. We need to log data from all the agents in a swarm and have like clear insights into what's going on. Then the second one would be task allocation. So how are tasks being allocated? There are many different types of task allocation we could do, and task allocation is like very closely tied with the swarm architecture. So so the swarm architecture is actually like very, very dependent, or like the swarm architecture will influence the task allocation. So an example, in a hierarchical swarm, kind of like a modern everyday corporation or company, like there's always going to be like the CEO or the chief executive team is always going to be allocating tasks down to the people below them, and that would be like a form of task allocation. Then there's others like a queen bee, like a queen ant hive swarm will have like the queen will allocate tasks to the ants, or kind of like in bats, like bats fly together. They're kind of like non-hierarchical, and they'll just do everything kind of randomly. There's no structure at all. It's pretty flat. So like task allocation is very, very closely tied with the swarm architecture. Now in our case, there's a couple of things we could do. So like when the user like has an inputs, when a user has an inputs or like a task, depending like if they just want to run it once and have the swarm try to accomplish a very big task at once, we can have an agent that will split up the user's goal into like 100 different sub goals, and then like it will assign certain agents those tasks, or the agents can kind of like pick up their own tasks and kind of like a combo board, or I forgot to say it, combo board, where you just pick up whatever task you want and it solves it.
Yeah.
Um,
yeah. I think one way to drive what you're talking about is GitHub bots. So I've seen this project that like if you add an issue, you can have a bot first take a look at the issue and try its hand at solving it, and if it can't, you escalate it to a person that could. So I think that's one way of adding that kind of functionality. I've never actually built a GitHub bot, but that might be something to look into.
So,
because like we've seen that like these systems do a good job at breaking tasks down to smaller and kind of knowing where to go from an initial vision, or I guess in this case prompt, that the higher the human would give, and then it can break that down, create issues, create combined boards.
yeah.
Yeah.
We gotta think harder. We gotta make like a space of all the different task allocations. We should work on the Figma and just try to map out our ideas for this, because there's a lot we need to find, or we need to find the best ones, like, or implement all of them and test them all. I definitely think a task allocation is going to be a very, very big, very, very important piece of a swarm. I think it's very important, and I think we're going to need to solve that before it really becomes super intelligence and can take over like a whole planet. um, I say that would be like a very important thing to solve now. Task allocation, how, like, yeah, collective fault detection. That's another one, dude. This little image right here should be like, kind of like a reference for like all the problems we need to work on, because like you have task allocation, then you have collective fault detection. Like, how do other agents know when you're wrong? That's a very, very big important piece of a swarm. So like when you write code, how do I know that your code is working, or how do I know my code is working and you don't tell me anything, and then we push code that doesn't work? This happened multiple times today. So
Yeah.
that's like collective fault detection is like, how do we know that the swarm is making sure that other agents in the swarm are making stupid decisions and like kind of destroying the swarm? So, well, obviously the swarm needs to survive to keep its objective. So if there's no fault detection, if there's no problem analysis, then that means that the swarm is at some point going to die, because it'll just keep making an infinite amount of mistakes, you know? So we also got to figure that out and figure out like maybe all the outputs and all the actions can just be outputted in the vector database. Like everything is just in the vector database, like all at once. Um, so like all the agents can see like everything that everybody's doing all at once. I think that would be like I think that would be pretty. That would be a pretty interesting way. Um, then, like, what do you think?
Yeah. So I think, well, I always try and think of like pursuable goals as well as stretch goals. I think for a minimal viable, something we could do now and we could do easily. Well, not so. Everything's so easy as you think initially, but we could do. One thing we could do now is create the. I think GitHub is a great place to manage something like this because it's got like the bond boards. You can assign issues to certain. We could make some GitHub bots, and we could there's this project for where the bot will actually pick up issues if assigned them. So that's one environment to kind of use for task allocation. Of course, we can use any of the other Kanban board services out there like Trello or Yeah, Trello or Jira. I imagine if we're going to be implementing this into small and medium-sized businesses, Jira would be a great platform to go after as well, just because it's widely used.
Yeah, that would be.
There is also the one you were suggesting.
That would be a pretty good idea. We can make we could actually just like we could well I'm gonna add now to the project board to add the I'm gonna make an Asana tool or like a Trello tool. Yeah, so like not even like all the stuff in like a company's Asana could be fed into like the swarm, like the swarm level embedding space, and like all the agents can have all the data that like then they get one task and they do that one task. Can you hear me?
Yeah.
So I think it was Llama Index or what used to be GPT something. They have a pretty good. They have a lot of good tools for this, so we can get started with them to make a tool.
Yeah.
I'll work on that. Yeah, I just added that into the project board.
Cool.
I'm gonna be
kind of taking notes too. So, but yeah, if you already added that to the project, then that's.
I'm gonna be adding in features. Yeah, that's a good idea.
All right. Self-healing, that would go into like the self-healing would be more like the reading its own debug.
Oh.
Like reading its own error logs, like an interpreter.
I don't think we finished. We were at collective fault detection, I think. Collective perception. That also goes to the orchestrator. So I think collective perception collective perception means being able to perceive with the entire collective. So like imagine you could see what I'm thinking, and you could we could see each other's thoughts. That's kind of like a swarm, so we would have to add collective perception, and it can't always be like communicational. It has to be something more abstract. That's what the vector embedding database does. It allows for collective perception. Now we can also do this with I think the embedding space is probably the best way of doing this now, because think about it, an agent can only talk to one thing at a time. So if you're talking with GPT-4, it cannot talk to someone else. There's only can only talk to one thing at one time. So the one thing that that it should communicate with at one time is kind of like another medium, or kind of like the vector database, or like some mechanism that allows for collective perception. I think that the embedding layer, like vector embeddings, is probably the best way of enabling collective perception. I can't really think of another way, unless that's probably I don't know.
So maybe if the agents could break down the tasks beforehand and share them with the other agents, so they're kind of all perceiving the direction that they're going to go, and understand what the other's kind of perceiving needs done, and assigning things that way. So maybe it's not just a group. Maybe it's not just a single thing deciding what needs done, but multiple agents can be involved in the planning phase as well. as far as like the level of abstraction, the level to enable perception for this, I think the embedding space is a good way um, to go about that. But I think on the level of like the agents themselves, we could, we have like an early prototype of the very manual right now, but it basically will just start up a Docker container with whatever instance of whatever. Well, right now you select it manually, but it would through it's the AI's reasoning figure out which agents it needs to start up and what tasks it needs to assign to them, or maybe just send the goal to them, and they're all involved in perceiving and uh, and I guess executing on the tasks. So
Yeah. Moving on, we have synchronization. That's another big problem. How are you is the swarm synchronized? How is it synchronized? Is it working on tasks that other agents are not working on? Does it have its own individual task that are they stepping on each other's feet? Um, what's how are they synchronized? Are they actually heading towards the user's objectives? How are they accomplishing that? I think that's another important question. We're probably going to have to add a task or an agent synchronization mechanism to make sure they don't get in the loop or start outputting a bunch of useless stuff or just not do anything at all. I think that's a really big, really big. That's a really big component of the swarm.
Yeah.
Then the next one would be group size regulation. I don't think. I mean, maybe if you have some constraints like computation or energy, then you would have to regulate the size of the swarm. You can't just let it scale for eternity. I think, yeah, you're gonna have to have it can't just be ideally in Kubernetes. A Kubernetes cluster is auto scaling, which means it'll scale however many times you want. So
yes, there was this engineering book that was talking about something like this, where having a larger team doesn't necessarily mean you're going faster.
Not at all.
Because there are points of communication. So one node in the group needs to communicate to every other node. And so you draw. I don't know if I've got one node would have to communicate to all the other nodes, and those would have to communicate to all the other nodes.
Yeah.
And the more nodes you add, the more lines of communication is exponentially increased, and every line of communication is a chance for something to go wrong.
Yeah.
So
more communication means more problems.
Yeah.
So group size regulation. Ideally, theoretically, you should only have a minimum amount of agents to complete a certain task. You don't want to maximize. Maximizing agents would be ideally this should be lean. Should be able to get things done with the most minimum amount of effort. and the most minimum amount of agents. So that's what I get from that.
Yeah.
Yeah, that's what
Plus,
I get.
like computational wise, you don't want to spend all the world's resources on a single project.
Like all the resources in the universe just become.
I guess if you think about it, that you would think you have got to think about it as like, so maybe in a way, if the project is Project Utopia, that you could spend all the resources on, but that would look more like them. Like what that would look like is actually just split into 100 million different projects. Projects for solving hunger or all these issues, project per issue, basically. But yeah, so computation is another thing to consider.
Yeah, then miscellaneous. Miscellaneous. Self-healing should be able to fix itself. What do you think about that?
Yeah, I think some ways to enable that is it, OpenTurbo reads its error messages, but also, learning from the errors of others too. So it could also see this agent went this route and did this before installing this package, and they got this error. So I'm going to make sure I install that package first. And so I think that way self-healing, it's hand in hand with error prevention as well. Yeah. And also like being able to restart if it needs to. So like, I don't know, can you like tell a Docker container to restart itself?
Yeah.
Okay. Yeah. So I mean, that's one way. If it had enough control to yeah.
Self-reproduction. I say that is also pretty important. So like in our case, we could just give we could give the worker like another worker to like self-reproduce. So that's what that would look like in real life. You just make a new function and you say this is a worker agent. You could basically reproduce yourself if you need to kind of like tackle a problem that is pretty complex. Then they can initialize like can you hear me?
Yeah.
Can you hear me? It's super laggy. Yeah, I'm still running the Discord bot. So something that they can do is basically we could have the worker. We can create a tool. We can create a worker as a tool, then pass that tool in to the worker, so it could just reproduce.
Yeah.
That would be very simple, and maybe we can even add another tool that basically like a tool that allows them to engage in a group chat.
Mm-hmm.
So
yeah, so as far as like self-replication, I've seen multi GPT and things do something similar. But yeah, if it has a large lists of tasks they could self-replicate to create more threads for execute solving those tasks. So it can scale up kind of like Kubernetes as it needs to, and then scale down. It should be able to scale to 0 and to infinity.
Yeah. Then the last.
Maybe not infinity.
Then the last thing, human swarm interaction. I think that's also not pretty miscellaneous. That's really important. There should be like a very easy and intuitive way of understanding what every agent in the swarm is doing, like all at once. So what that could look like in a terminal, would be like you just have like every agent would have their own line, and then it would say what task they're working on, like task completion ratio with like a loading bar. That's kind of like what the UI would look like in the beginning. Or in a UI, like the platform that we're going to create, we could like the build and drag and drop and graph like swarm platform. You could just click on an agent and see what they're doing. Ideally, that's probably another way. But I think the whole purpose of a swarm is to serve humans. Let me make that very clear. So we need to make the experience easy and reliable, and provide an overwhelming amount of useful data to the user so that they can optimize the swarm and do what they need to do. So like you should always be able to like manually take control of the agent. Like if like let's say in the robot mining in the moon scenario, we could have like an interface where you just click an agent, then you could see like the vision, kind of like a GoPro first person viewpoint of what the agents are perceiving, kind of like a video. Then like you could say like take control of the agent. You could then take control of the agent yourself. Yeah, I think those are some ideas on that.
Yeah. As far as like the best way for a human to interact with another swarm, yeah, I think it would have to be you would be talking like you would talk to the highest level of the swarm at first, and if everything's running smooth, like you shouldn't need to keep tabs on all the other agents, but you should have the ability, of course. But for ease of interaction when everything's running smooth, you talk to just the main agent, delegating and summarizing what the other agents are doing. And then you can take finer granular control, pilot a robot mining on the moon, or just shut down a rogue robot, or even if the orchestrator has the ability to do that. Just alignment is probably key as well for human swarm interaction. That's probably the key, maybe the key to alignment. It is to serve humans first.
Yeah. All right, let's move on.
Yeah, let me finish this now for a second. Spatial organization. These behaviors allow the movement of robots in a swarm environment in order to spatially organize themselves objects. Aggregation moves the individual robots to congregate spatially in a specific region of the environment. This allows individuals of the swarm to get spatially close to each other for interaction. Pattern formation. Pattern formation arranges the swarm's robots in a specific shape. A special case is chain formation, where robots from a line typically establish a multi-hop communication between 2 points. Self-assembly connects the robots in order to establish structures. They can either be connected physically or virtually through communication links. Special case is morphogeneous, where the swarm evolves into a predefined shape. Object clustering and assembly lets the swarms of robots manipulate spatially distributed objects. Clustering and assembling of objects is essential for construction process. Navigation. These behaviors allow the coordinated move of swarm of robots in the environment. Collective exploration navigates the swarms of robots cooperatively through an environment in order to explore it. It can be used to get a situational overview, search for objects, monitor the environment, or establish a communication network. Coordinated motion. This moves the swarm of robots in a formation. Formation can have well-defined shapes, example a line, or be arbitrary as in flocking. Collective transport. By the swarm of robots, collective transport by the swarm of robots enables to collectively move objects which are too heavy or too large for individual robots. Collective localization allows the robots in a swarm to find their position and orient relative to other via establishment of local coordination systems throughout the swarm. See section 2.2 for more details. Decision making. These behaviors allow the robots in a swarm to take a common choice on a given issue. Consensus. Consensus allows the individual robots in the swarm to agree or converge towards a single common choice from several alternatives. Task allocation assigns rising tasks dynamically to individual robots of the swarm. Its goal is to maximize performance of the entire swarm system. If the robots have heterogeneous capabilities, the tasks can be distributed accordingly to further increase the system's performance. Collective fault detection. Collective fault detection within the swarm robot determines the deficiencies of individual robots. It allows determining robots that deviate from desired behaviors of the swarm due to hardware failures, or I would add software failures as well. Collective perception combines the data locally sensed by the robots in the swarm into a big picture. It allows the swarm to take collective decisions in an informed way, classifying objects, reliably allocating an appropriate fraction of robots to a specific task, or to determine the optimal situation to a global people. See section 2 for more details. Synchronization aligns frequencies and phase of oscillators, a phase of oscillators of robots in a swarm. Thereby the robots have a common understanding of time, which allows them to perform actions synchronously. See section 2 for details. The desired group size regulation allows the robots in the swarm to form groups of a desired size. If the size of the group exceeds the desired group size, it splits into multiple groups. Yeah, so like they can be working for the same outcome. If like the outcome is utopia or something, then they would split into other groups for tackling this issue. To bring that about. Miscellaneous. There are further behaviors in swarm robots that fit either. There are former behaviors in swarm robots that fit neither the categories of self-healing allows the swarm to recover from faults caused by deficiencies in individual robots. This goal is thus to minimize the impact of robot failure on the rest of the swarm and to increase its reliability, robustness, and performance. See also collection fault detection. See section. Self-replication allows a swarm of robots to either create new robots, replicate the pattern created by many individuals. The goal is to increase the autonomy of the swarm by eliminating the need of human engineer to create new robots. This section. Swarm intelligence, swarm interaction allows humans to control the robots in the swarm or receive information from them. The interaction can happen remotely through a computer or proximal in a shared environment through visual or acoustic clues. But, they came closely to the ideas we had. Some things they've added that at first we didn't think of were one that struck me was the cluster assembly. So they can have predefined one, like they kind of already know that, like birds kind of already know that the flocking pattern, they've found that the V works best. So maybe there can be predefined ones, but they can also be using exploration to find other optimal formations as well. A detailed description of additional swarm behavior categories. In the following, we describe additional categories of basic swarm behaviors, which we extend to taxonomy by namely collective localization, collective perception, synchronization, self-healing, and self-reproduction. The collective localization. Collective localization allows the robots and swarm to find their position and orient relative to each other via establishment of local coordinate systems through the swarm. Sources of inspiration. This approach given below the approaches given below are engineered without any mentioned inspiration. Okay, I don't know if I'd agree with that. Everybody has drawn inspiration from something, these, like, your success is never your own. It's always, the people before you or the people allowing you to, like, I think, I don't know if I agree with that. But I guess in the form of, like, they're not citing any other articles that fine. Approaches. There are two approaches which originate from multi-robot research domain. First, creating a map of the environment and localizing relative to it. This approach is called simultaneous localization, and that means SLAM. It can be used and can merge different sources of information such as marine sensors, visual sensors. Second, using stationary landmarks with known positions and localizations relative to them to avoid relying on external information. Other robots can be used as landmarks. The robots can move alternatively through the environment while keeping precise localization information. If the initial position of the robots are known, then also absolute localization is possible. The dead reckoning approach, where robots use odometry for localization, is another possibility, but introduces an accumulating error which renders it useless for most scenarios. So I would say that having them share kind of a vision or be able to, understand or, see like a combined perception would help with this as well. They would be able to see through the other robot's eyes essentially and see the landmarks there for localization as well. Results. Thorne presented a mapping algorithm where multiple robots can localize in a global fused map. It requires the approximate initial positions of the robots are known by all of the robots. It uses an incremental expectations maximum approach, which allows the robots to localize themselves into maps created by other robots. Experiments demonstrate that the robots can localize robustly in real time in large-scale environments using low-end computers. In the follow-up work, the requirement of known positions is relaxed, assuming that robots share an overlapping part of their explored maps. It employs the concept of information filters that represents the robot's positions by the Gaussian and Markov random fields. The robots are able to identify the correct alignments between different local maps by maximizing the correspondence of similar-looking landmark configurations. Fox et al. 2000 presents a brief-based approach of collaborative multi-robot localization. It fuses localization and forms information from different sources such as odometry, environment measures, and multi-robot detections by combining visual and range sensors. This allows to improve the robot's belief in the world by learning the detection model from data using a maximum likelihood estimator. Experiments demonstrate that the team of robots is superior in localization compared to single robots with a relatively small communication overhead. Kusami and Hiros 2000 proposed the method of cooperative positioning using robots as landmarks. There are two groups of robots to move alternatively while using this other stationary group as a localization reference, and an increased number of robots also increases the redundancy of positional information. With the weighted least square method, this redundancy decreases the localization effect. The author performs experiments where the robots use range sensors to measure their respective positions. Results show that this localization method performs better than the dead reckoning method, including environments with unseen terrain. Rakowski, 2001, proposed a method where robots visually observe each other to improve the dead reckoning localization. They proposed two algorithms based on triangulation, trapezoidization for small and large scale environments, respectively. They perform experiments with two robots where one robot carries markers and the other a camera. The results demonstrate the joint localization leads to more robot localization than odometry alone. When more robots are used, the localization precision is increased. Howard et al. 2003 proposed a maximum likelihood method combined with distributed numerical optimization to eliminate the need of landmark robots to be stationary. It combines ranged methods with odometry. Robots observe each other's motions and exchange this information to create a graph consisting of their positions and respective observations. Experiments with 4 robots demonstrate that this method is able to localize with adequate precision and is robust to change the environment, to changes in the environment and to flawed geometry. Furthermore, robots are able to control the position of other robots they have seen before. Rubinstein, 2014, applied a robot landmark approach to a large swarm of 1,024 kilobots.
Jesus.
That kilobots, I've never seen that before, but you're going to have
You should look it up.
kilobots instead of it's kilobytes. Yeah. The kilobots. Kilobots is a swarm robot. A kilobot is a 3.3 centimeter tall, low-cost swarm robot developed by Robotic Newpod. Robots. Oh, wow.
Jesus. Made a K. Dude, that looks insane.
That looks so much fun. I want one.
Yes.
It looked like relatively cheap to build, too.
Dude, this is hilarious.
Kilobot. Stop organizing from system for research. The kilobot is swarm of 1,000 robots, 10,024 swarms designed to allow one to program and experiment with the collective behaviors of large-scale tasks. Each robot has the basic capabilities required for autonomous swarm. A programmable controller, basic localization and local communication, but is made with low-cost parts and mostly assembled by automated process. In addition, this system design allows a user to easily and scalably operate a large kilobot collection, such as hands-off programming, powered on and charging all robots. We use the kilobot system to investigate collective artificial intelligence. Example, syncing, collective transport, collective assembly, as well as to explore new theories that link minimal individual capabilities to achievable swarm behaviors. By using a combined theory experiment approach, we aim to develop new algorithm insights into robustness, scalability, self-organization, and emergence in collectives of limited individuals. Which other topics of work. Okay. That is cool. I want some so bad. I want gigabytes of kilobytes.
How much do they cost? Yeah, I don't think they're for sale.
No, you gotta buy them and build them. The BOM for each kilobot includes a custom printed PCB, microcontroller, the AT Meta 2003, that runs through my microcontroller, a vibration motor that allows the bot to move by skidding on its 3 middle legs, rechargeable lithium battery, an hours of charge, photo translator that detects infrared light signals from other robots, or an overhead controller, 2 LEDs that indicate the robot's state and provide feedback to the user, switch turn off, a charging connector. The cost of each kilowatt is about $14, making it one of the cheapest robots available. The cost of 1024 is $14,336. $14,360. However, this does not include the cost of the robotic controller, which is a separate device that can send commands and a monitor for the swarm. The overhead controller support infrared receivers, a camera, a computer, and a computer. The cost of the overhead controller is not specified in the source and is likely to be much higher than the cost of the kilowatt. I'm unable to find. Okay. Normally, when someone provides they provide it as like this.
All right, let's move on.
Well, yeah. Collective perception. Collective perception combines the data locally sensed by the robots into the swarm into a big picture, which allows the swarm to make collective decisions in an informed way, to classify objects reliably, allocate an appropriate fraction to the robots to a specific task, or determine the optimal situation for a global problem. Sources of inspiration. Many social insects are able to get a global view using only local information. Examples are honeybees that assess the current global workload balance by evaluating simple cues like queuing delays and using pheromone trails to find the shortest path in the environment. Approaches. For collectively determining the type of objective observed, the paradigm approach is the classification of the object among a set of predefined modes. Sometimes the mobility of the robots is used to improve the perception of individual robots. The robots use explicit communication in order to propagate their findings and achieve the consensus. The way the robots exchange the information is an important aspect. They have to add the contextual information that allows the other robots to correctly interpret the data. Furthermore, the information can be simply forwarded, thus spread into a form or modified in order. Example, to measure the distance to a specific location. There are also approaches for other research needs, such as camera networks by Scrice and Renner. For the robots, the agents are typically stationary and often centrally controlled. Results. He proposed a strategy where sensing agents collect, analyze, and categorize data, enrich it with contextual information, and forward it to a synthesizing agent. The latter are then able to use the different aspects observed by the sensing agent to perceive events using an space method. Using simulation experiments, the author demonstrated the events can be detected reliably using only the first few Ignigen values. Cornesco, 2005, developed a form of micro-robots for collective classification tasks. Based on the evidence theory, the swarm has to identify the geometries of the objects in a space by exchanging data from infrared depth sensing while having limited communication capabilities. Experiments show that the wrong belief on an individual quickly converges to the correct belief after exchanging a few messages. King of Breeden presented a simple model of hexagonal grid world in which swarms have to different between different shaped objects. They show that an increased number of agents leads to an over-proportional decrease of object detection time. Gaussian presents an approach for cooperative gesture recognition with its robot swarm. Each robot processes and classifies camera images locally using a distributed consensus protocol. The robots exchange their options over a low bandwidth wireless channel to find a common decision by exploiting the different views and mobility of the agents. The approach is evaluated through simulation and physical experiments on 13 robots. The results show that the recognition of accuracy of the system scales efficiently with the number of agents and is robust to communication failures. Gano 2014 developed a method that allows swarms of robots with different types of low-resolution sensors to collectively classify objects. Each robot processes the sensor data locally and exchanges its estimation. Using the naive Bayes classifier, together with the information received from other robots, the swarm is able to robustly classify objects. The more diverse the sensors are, the better the results. Afati Saver and Jamal presented a theoretic framework that employs mobility to improve the information sensed by the swarm using the Kamal census filter. It is employed to track a target of the swarm of agents. Each agent then tries to improve its sensing while avoiding the collision with others. Simulations show that this solution can effectively track linear and nonlinear maneuverable targets. Marsden and Renner presented a method for simultaneous convergence of surfaces with swarms of. This method assigns robots to different viewpoints in order to allow 3D reconstruction of objects. Simulation results show that the method is able to coordinate the robots while minimizing the mission duration and maximizing the coverage quality. Umico 2007 compared different communication strategies for collective perception of the swarm, namely the hop count strategy and the Trafalix inspired strategy. The presented solution allows the swarm to collectively compare sizes of target areas which are too large for individual robots to perceive. Simulations show that the robots are able to aggregate in the target areas while the numbers are proportional to the size of the target area. Mound and Evans tackle a similar problem in which robots should distinguish good and bad spots using models and chemical reaction networks. They perform experiments with 5 robots and demonstrate that robots with limited sensing capabilities can collectively achieve good performance. Synchronization. Synchronization aligns frequencies and phase of oscillators of the robots in the swarms. Thereby, robots have a common understanding of the frame which allows them to perform actions synchronously. Sources of inspiration. During courtship, males of a certain animal species synchronize their behavior. In some firefly species, a phase differ between the blinking of male and female flashing light periods is important for mating. Hence, fireflies synchronize by influencing their phasing flashing phase. Likely, the brush crickets synchronize or alternate using chirpings by learning their chirp methods in response to other chirps. Bart Bauer, 2005, and Ignash, 2001, developed a model that describes the spatio-temporal wave patterns observed from mycobacterial cells. There are many more examples of coupled oscillating systems. Example, pacemaker cells in the heart. Liskin, 1975. Or clapping of vectors in the theater. Approaches. The oscillators are synchronized to the same frequency, with the phases being aligned among the robots in the swarm. Two approaches exist. Either the oscillators continually influence each other to adjust the phase of frequency, or the close coupled, meaning that they are regularly fired and a signal corresponding to their current phase. The later one is mostly used as it requires fewer interactions between the robots. Robots interact through their acoustic, visual signals, or radio controllers. Results. Bauer and Rober employed synchronized oscillators as a communication and navigation system. In a synchronized system, robots at a target area increase their frequency and thereby produce phase waves in the swarm that can be used by the robots to perform wave-font navigation. Travel towards higher frequencies. The authors analyzed the robustness of the system by simulating up to 300 robots. The results show that this communication system is robust. Changes in signal strength, signaling method, signaling period length, and communication objects. Nevertheless, the signaling period is an important parameter to fit the scenario. They conclude the pulse-coupled oscillator synchronization is especially suited for swarms as it has low hardware requirements in terms of communication range and processing power. Christine, 2009, applied synchronization to detect faulty robots in the swarm using pulse-coupled accelerators and visual signaling. The swarm can determine malfunctioning robots when their phases are not aligned to the rest of the swarm. The authors developed the discrete models that can be applied to the swarm. Simulation with 100 robots showed that the robots synchronize faster than they are coupled. Synchronization time is linearly proportional to the swarm size, where denser networks synchronize faster, and synchronization is robust to communication objects, but decreases in performance. Experiments with 10 physical robots confirm the simulation result. Despite the inherent latencies associated with the sensor actuator systems, in contrast to bio-inspired approaches, Greeny and Nolfi synchronization synthesized synchronization strategies using artificial evolution. These strategies perform phased coupling between robots in order to allow synchronous movement. Simulations with up to 96 robots show that the strategies scale well and are mainly limited by collision avoidance behaviors. This is confirmed to the experiments with up to 3 robots where sensors and actuator noise is introduced. Bezo synchronized robots in a swarm to determine the network topology and detect changes. They developed a strategy for estimating the degree of accelerators coupling in the swarm of synchronizing them continuously. Applying this strategy to the formation control allows 3 simulated robots to move in a formation. Simulations with 5 robots show that the network topology can be detected reliably. Garces applied the novel concept swarmulators. That's a new one. Swarmulators. Swarmulators are oscillators that swarm. They can swarm as well as sync a dynamic balance between their spatial proximity and phase similarity. And there's a paper on this. Swarmulators.
That's interesting.
That's a great name. I'm gonna post this in papers.
Yeah, I was going to say that's really funny.
Formulators are we already read. Well, it did kind of. Formulators allow for modeling complicated processes such as flocking, schooling the fish, cell sorting, and robotic development. Residential segregation and optimal dynamics in social groups. We demonstrate the versatility by capturing maneuvers in a school of fish, traveling waves of gene expressions, both qualitatively and quantitatively, and broad cell sorting, microbot collectives, and various life stages of some slime mold by a suitable extension of the original model, incorporate features such as gallery of its intrinsic self-organization and various interventions. But the high-level dimensional model may be potentially used in developing swarm systems with a wide range of disciplines, including physical and active matter, development, biology, and social engineering. This concept couples the actuator phase with the spatial localization in a way that allows them to mutually influence each other. They modify the original model by taking into account the strict natures of the robot. Simulation of 100 robots experiments with 10 robots show that spatial temporal patterns can be performed in stationary and symbolic scenarios. Synchronization capabilities of the swarm altering the field of interaction and the speed at which the robots travel. The emergence of synchronization can be influenced. The robot speed influences the time until synchrony is reached, whereas a narrow field of interaction results in a low degree of synchronization. Furthermore, high robot densities limit the synchronization ability due to signal occlusion and collisions. Self-healing. Self-healing allows robots to recover from their faults by the deficiencies of individual robots. The goal is to minimize the impact of robot failure on the rest of the swarm to increase its reliability or robustness. After detecting the fault, the appropriate countermeasures must be taken. sources of inspiration. The immune system of invertebrates shows how biological systems protect complex organisms against disease. This serves as an inspiration for artificial immune systems, AIS. Bemis gave an overview of how EIS and swarm intelligence relate. They point out many similarities and conclude that both systems are complementary and tools for solving complex engineering problems. Regeneration in global systems allows animals to heal their body. Examples: salamanders, starfish, lizards are able to regenerate their lost limbs. Another prominent example is the thalamus, the tissue regeneration of the Nargian hydra. This Nargian hydra. It's some water plant. It exhibits that it sometimes is referred to scalable self-healing. When the hydra is dissected, each part can self-heal into a fully functional and independent hydra where its size is proportional to the numbers. So, similar to hydra's splitting heads. So maybe if it fails on a problem, it can split heads. It can create more swarms to tackle that problem. If the problem is not having enough members on the swarm or on the problem results.
That's interesting.
As self-healing, yeah. As self-healing is relatively challenging topic for swarm robotics. Only few embodied studies exist, and most work is done through simulation results. DI presents a model for detecting and healing software components of swarm robots. This part of the NASA Autonomous Nanotechnology Swarm ants. The ANTSCOM mission, the swarm concept mission. This 2012. This model is only partly distributed as it relies on a central cyber disease library. Each robot runs one or more virtual neurons as a background process. They monitor certain system variables such as CPU, memory, and network usage. But the thinking of this is like the components that make up the robots. It needs disease library. It can understand through a disease library if it's a hardware error or a software error. That would be it's interesting. Each robot runs one or more virtual neurons as a background process. They monitor the system variables, network and CPU and memory usage. In the case of anomalies, it freezes the process in question and reports its behavior to a higher level controller. It can perform further diagnosis by assigning more neurons and generating prescription based on the cyber disease. The prescription is applied by the actuator process, which reports back results. This allows the cyber disease library to learn and improve prescriptions. So what would a cyber disease library like? What is there, like Stack Overflow, or I guess just the internet in general?
Can you say it again?
What would a cyber disease library like? I guess just a data set of issues with the
I don't know.
the fixes to those issues.
I don't know.
And then maybe train like a doctor AI model to prescribe the fixes and the or whatever disease they're reporting. In this case, the prescription does not work. Further escalation steps are possible, and such killing the faulty process or even rebooting the whole machine. Simulation case study shows the memory leaking process successfully detected and eventually leaked. The result shows that the system becomes more reliable and robust against failures and failure propagation. Even through faulty processes, creating the overall system performance. The performance improves compared to systems without self-tailing produced. Venus applies self-healing to overcome applying self-healing to overcome hardware failures. They present a solution that is inspired by granulum formation in a process of what is granulum formation? Granulum formation are organized. Granules are organization conglomerates of histiocytes, a special of that's what it applies to in the biological sense. But in the sense of a swarm, that would be where are we? They present the solution that is part of the granulum formation process of containment and repairment found in the immune system. They apply to the swarm robots performing flocking and taxis towards the beacon. When a robot has a discharged battery or loss of mobility, it could anchor the whole swarm. It would anchor the whole swarm, which would then fail to reach the beacon. The proposed solution allows the energy sharing between healthy and faulty robots. Faulty robots signal their need to the other robots within range. Depending on the required energy, the energy available of the healthy robots and the varying number of robots surrounding the discharged robot to share energy. Other robots ignore the robot cluster and regard it simply as an obstacle. Continuing their mission. Simulation experiments with 10 robots show that granulum formation works well even when half the robots in the swarm are experiencing low-level energies. Other algorithms are compared where only the nearest healthy robots perform the healing. They fail to heal the swarm when 3 or more robots have a discharged battery. The broad body of research is directed towards a pattern formation and morphogeneous self-healing. Proposed by the shape rules approach, where agents evenly disperse within a predefined shape. First, the agents perform triangulation to establish a common coordinate system. This is aided by following a few agents to know their initial position, and then the agents use the contained gas model to move in a way that they are equally spaced within the desired shape. In the case of the agent failure, the other robots simply adapt their positions to again reach equilibrium density. The agent model contains a proximity sensor and a wireless communication to exchange positions. It furthermore requires the compass to determine the global orientation of the agents. Simulations show that the swarm can self-repair and established in classes of agents help agents adapt for displacement. Furthermore, it can overcome large degrees of sensory or movement errors of the agents. Rubinstein and Shen relax some of these assumptions and still achieve similar results. The model differs in the robot build as the robot builds compact shapes. Thereby, the size of the shape varies rather than its density. The model requires only a single sensor for local information and communication. Shape is then given to the robot as a potential field where the robots aim to move towards its center while avoiding collision. The shape of the scale is calculated as a function of the estimated swarm size. Additionally, each robot changes its color to a color that is predefined depending on the position, whereby the robot can form color patterns or displays when properly synchronized, and they can even show time-varying patterns. Simulation results show that the robots can perform scalable self-healing by recreating the desired shape for varying swarm sizes. In later work, Rubinstein demonstrates that this is a large swarm of physical robots as described. Robotic and Richa propose an external compilation process that uses the polygon to determine the set of parameters. The local rules to be executed by the swarm of homogeneous stateless robots by attaching physically to each other when the robots can communicate directionally. You can stay connected as long as they are communicating by replying with predefined messages. State of the system is externalized and circulating messages attaching to each other. The agents curl the edges of the polygon or randomly entering robots diffuse into the interior of the polygon by replacing boundary robots that in turn move into the polygon interior. Simulation experiments showed that the swarm can build simple polygons and can heal from failures due to the communication, such as dropping messages. Robots that do not communicate anymore drop out of the shape and are replaced by new ones. If the shape is broken into two, the robot creates two shapes with the original size. Self-reproduction. Self-reproduction allows the robot swarms either to create new robots or replicate the pattern created from many individuals. In the first case, the robots produce identical copies of themselves. The goal is to increase the autonomy of the swarms by eliminating the need of human engineer to create a new robot. In the second case, the robots copy a structure consisting of many individual robots. Existing approaches are not fully autonomous yet and typically require at least building blocks to provide the swarm. In contrast to self-configuration of formed patterns, the goal of self-replication is to assemble a functional robot from passive components. Forces of inspiration. All biological processes possess the ability to reproduce either sexually or asexually. Approaches. The theory of self-reproducing machines already exists for several decades. Limian introduced the idea of the Talentog model for self-reproduction. The research in this direction allows a general idea of template reproducing systems, i.e., to create new robots according to an existing model. Gross and Virgo give a historic overview of the developments in this direction. Other approaches follow the evolutionary design strategy. The existing approaches assume the robot hardware to be modular in order to have a base building block. The finer the modules, the more difficult the process, but the more flexible of a new robot. the more flexibility of the robot can be created. Results. Within Tolnak evolved the design to a simple electromechanical system through simulation experiments. The building blocks are bars of actuators that are connected through joints controlled by the artificial neurons. The performance of the evolved systems is measured in terms of distance and is able to look common. The best performing designs are fabricated using rapid additive manufacturing technology. This process allows robots to design new robots with minimum human intervention. The manufactured robots are able to locomate similar to simulation models. Booth Warren presented a fully autonomous self-replicating robot built from Lego parts. It assembles new robots from 4 pre-assembled subsystems that hold together using magnets and shaped consisting music blocks. The controller of the replica is already pre-programmed with the same program as the original. The experiments show that the original robot, which is guided by the lines on the ground, is able to detect the subsystems and assemble them into a fully functional replica. So my thoughts on this are, we're building the building blocks for building agents, more specifically swarms of agents. If we were able to train a model on our own framework so that it understands how to build agents and more importantly when to build agents, it could build its own unique agents or even predefined agents like what they're doing here, or any kind of task that they need done, or even for like an evolution process. So if it needs to build a better version of itself, or combine parts of other systems to build a better robot. Zakov presented the design of a modular robot cube called the Mole Cube. These cubes can attach to each other using electromagnets and hence form complex patterns. These cubes have one actuated degree of freedom to control the shape of the assembled pattern. The authors present experiments where the spatial patterns and corresponding controllers are both manually created and automatically designed with artificial evolution. The results show that the swarm of both cubes reproduce identical copies of its pattern both in simulation and physical experiments. The only human interaction is providing enough molecules as a building material. The authors conclude that the more units that are involved, the simpler and more homogeneous they are. The more information is being reproduced by the system itself as compared with information pre-existing in the piece of paper. Look at these long cubes. Some more cubes in action. More cubes are the building blocks that can. They are made of 2 rotatable halves, microcontroller, and a motor for rotating. The robots construct entirely new null cubes and create copies of itself in a number of cubes. So yeah, it seems most of this paper has been focused on the hardware side of things, but with what we're building with swarms, we'll focus more on the software side of things, and I think that's important, an important aspect to focus on, because you can always simulate hardware interactions through software. And I think if we make the mole cube, well, the software version of the mole cube, and allow agents to not only understand but combine different components, I think we'd have a good system. I'll be right back. Just a fat break.
Oh, Zach. Hello? Zach, are you here? Avalon, are you here? Guess not. It's just Kai.
I'm here, Kai.
I see. What do you
What
think?
happened to Zach? I think the paper's good. I think there's a lot of specific experiments and examples to try, which gives a research plan. I think there are some gaps, though I don't have anything I can comment on right now. It is a lot to chew on. What do you think?
It is a lot to chew on. It's supposed to be like that. That's supposed to supposed to be like a survey of some kind. Talk about the problems, some solutions, and there's a lot of problems. And some solutions.
We are very early in the science of creating these sorts of systems. But they can be very powerful and might be quite the thing. If he were here, you'd know what he'd say.
I'm creating, trying to implement swarm relators now. It is a little bit difficult, but swarm relator. Hello, Zach.
Hey.
Yo.
1 second.
Thank you for reading, Zach.
Thank you, Evelyn. I had some notes I wanted to finish.
department.
Is everything good, Zach? Are you?
Yeah, just finishing up this last note here. Unless someone else wants to read this section, I'll finish this up.
Avalon, would you like to read?
Not particularly. I'm on my phone.
Nice.
Alright, swarm applications. Even though Swarm's robotic is a relatively young field of research and has not yet been widely accepted in the industry, this section is a first collection of existing application attempts of swarm robotic products. Swarm robotic researchers have designed and developed a number of platforms to test and analyze swarm algorithms. In their publications, the authors always stated their attempt to envision future industrial applications out of simplicity of swarm robotics research platforms. Thus, we split a survey into swarm robotics research platforms and an industrial project and products. The industrial projects and products are mainly listed to serve as application examples in real-world environments. Above a technology readiness level, TRL, of 4 were validated of the platforms in which are ready in the relevant environment. The research platform enables researchers to verify their demonstration and examples with swarm algorithms in the laboratory environments. STLR, ATLR, taxonomy 4. We'll look at this. Table 1 is the classification and research platforms of swarm robotics. So here, okay. So here we have terrestrial, environment, aerial, aquatic, and outer space. So here in the terrestrial, we have kilobots, Jasmine, Alice, Emmer, Alice, Mother. And if we could find links to some of these projects, that'd be great. But this is in the research and education realm.
Let's go to Let's do some of the more practical ones, not in research.
I like this one, swarmies.
Yeah, try looking this one up.
Yeah.
Swarmies in space.
Yeah. Let's see. NASA's army of swarmies.
Shit, NASA's already beaten us.
Yeah. Okay. These are self-driving swarmy robots. They can be used to search alien surfaces one day. So there's like open control tracks. But the truth is this: robots could be one day race across distant planets in this sort of space exploration vanguard.
That's it? Fucking dump trucks? Those aren't that bad. I mean, that's like a little toy thing.
Yeah.
That looks like a toy you give to your children.
Mm-hmm.
I think spider bots would be much better than those. They could be the same size, but I think spider bots would be more agile, and because the shape of the dump trucks, I'm gonna call them dump trucks because they literally look like a dump truck. It's not good.
Yeah.
So, can you look up what was it? Crazy Fly.
Yeah. Crazy Fly.
Swarm.
Swarm. Oh, these little things. Yeah. An open source project. Let's see, what is it again?
Look right
Crazy
there.
Swarm 2.
You missed it. There was a link that said Swarm. Yeah, so right there, go down. Right there, University of Southern California. Oh shit, robot disco. Swarm droid disco. Dude, check this out, bro. This is insane. Yo, check this out, bro. This is a pyramid. I wonder if they have to be pre-programmed to do all of this, it's useless. There should be like, can you go down? Alright, let's get out of here. Oh, check this out. But what the fuck is he holding? Look at that. It should be able to just detect it's a human and get out of the human's way. There should be like a massive embedding space.
Yeah. That's all.
Alright, let's go back. Can you go down a bit on the right? Go down, go down. Can you go down?
Yeah.
No, on the right.
Oh, projects, official NASA swarmathon.
That's just one project.
Is it?
Maybe.
Project official.
Alright, let's go there.
Maybe. Okay. Swarmathon.
You could have just clicked on the link.
Can I? If it's
Yeah.
an image?
Oh, you can click on the left. Oh, actually, no. There isn't. Just nasaswarmathon.com.
NASA swarmathon. Here. NASA swarmathon.
They only got $2,000? That's useless. Should get millions. Yeah, this shit doesn't exist anymore. Let's just go back. It's useless.
Yeah.
They wrote a paper on a hackathon.
I guess so.
This is insane, man. What the fuck?
Huh. Okay. I think we're probably just gonna have to, maybe they provide some of the prototypes built in here. Yeah, there's GitHub links. Lots of GitHub links. A couple GitHub links. Oh. Okay.
Polybot. Can you look up Polybot?
Refusing large data sets due to crucial vision-based modeling manipulations to everyday scenarios due to the selection of data set. Code for this? No.
Can you click on the paper?
July 2003. Yeah.
Can you go down? I want to see the diagram there.
Yeah.
So they do like 30 bots.
This diagram?
Yeah.
Okay.
That's interesting. Observations, action, alignment, image server, shared environments, robot specific controller, internal representation alignment. This is pretty good.
Yeah. Yeah, definitely. Very interesting.
Domain alignment.
Oh, this is a long paper. Where was there? Oh, okay.
Oh, shit.
Oh, there's so much.
Dude, look up offset by offset swarm.
Offset one?
Yeah. Military. Military got 250 of them. What is this?
Offset one?
Yeah, check out the images.
Oh.
I don't think, is this it? Try to go like one of the first ones. Dude, if these are manned military drones, can you go to the second image? The second image? Or, yeah, can you click on that link on the right? No. Yeah, the next, yeah, that one. No, not that one. The back one. Go back. Yeah. Click on the
This
top.
link?
Yeah. keep in pace with technology. All right, let's go back. So offsets. Okay, can you go back to the last image? No. I mean the last diagram. Yeah, table 2.
Table 2.
So damn, yeah. Let's pick a robot here. So they have basic entertainment. They have entertainment, drones, aggregation, pattern formation, coordinated motion. Can you look up Swult? Look up Swult swarm.
Okay.
Swilt. I. No, you.
Float.
Swilt. Yeah.
Industrial flag. Overall.
Can you go down? Alright, useless. Let's just go back.
Both research platforms and industrial products are categorized according to the environment they are used in: terrestrial, aerial, aquatic, or space. All of these tables listed of the type of the application, project, or product type, the type of robots and the robots form basic swarm behaviors corresponding to the definition of the section. Type of robot corresponds to one of the following categories: unmanned ground vehicle, UGV, unmanned aerial, AUV, unmanned surface, ASV, unmanned underwater, UUV, or general, USV. The number of research platforms used in swarms is proven with a specific research publications for the research swarm applications. We refer the reader to the products or the projects or product website for this information. For each research platform, industrial, project, or product, we list one or more basic swarm behaviors because no project or project that uses the internal swarm algorithms. They rather use parts of the algorithms and adapt them to the underlying application. Additionally, the table for the research applications differentiates between open source, hardware and software, or commercially available. We do not classify the swarm robot platforms and products related to their price, dimension, and number of usage in different research and engineering projects. The focus of this collection is on basic swarm behaviors embodied broken. Therefore, we only list product or projects that are based on the robotics platform. We neglect research projects that fully focus on swarms with a pure theoretical or virtual nature. Research platforms. This section represents search platforms that are developed for educational and scientific purposes. Organization of Table 1, they allow the investigation with the application of swarm algorithms to robots. Note that other sophisticated robotic research platforms exist, which are not included as they are not developed with the intention of using them in swarm applications. The Bamboo Robot Kit. Bamboo Robot. Oh, hey. We're on the footnotes. That's true. Kilowatt Swarm is probably the best known swarm of robots involved for research and education. Kilobots are very small, the diameter 3 millimeter. The localization is based on vibrating motors, and the communication is implemented using infrared lights reflecting off the ground. They've become very famous for the self-assembling capabilities, forming different shapes with swarms of 1,024 kilowatts. The kilowatt is available open source and commercial. The K-team. Phasmid is another widely used swarm robot platform. The open source platform was mainly built for large-scale swarm robotic experiments, equipped with a series of sensors using touch, proximity, distance, and color sensors. The intention for the scale of swarms is also components with the swarm robotic platforms. A series of research platforms building on each other is given with the AMIR, also open source and commercially available in Mona open source. Platform R1 is designed for the usage of swarm robotics platform, and it also uses gamma tracking system for ground truth localization. Ground truth localization. Many other sensors, including linear cameras, is extended for the base capabilities. A research platform is building off others is given in here. Cameras use transfer information. They connect all the pieces together for similar experiments, close to the swarm intelligence can be formed. The LSF3 swarm robotic platform is an open source. It also uses the Arduino microcontroller with a number of sensors, including IR sensors, 3-axis accelerometers, and ground flow sensors, and is able to recharge autonomously using a charging station. The robots of the swarm communicate either IR or radio. The Casper 4 is designed as a mini for any indoor lab application. A Linux core, color camera, LAN, Bluetooth, USB, accelerator, gyroscope, and microphone, loudspeaker, LEDs, and improved pedometry makes it compact and complete research platform for swarms in different scenarios. The Casper 4 is commercial, and the GridBot is open source robotic platform used in the Roboticarium, a Georgia Tech. The Robotarium provides remote access for large teams of robots. Scholars can upload code to run experiments remotely, collect data. Features like automatic registration of robots within a server, autonomous charging, wireless code upload for the robots, and automatic sensor collaboration makes the autonomy attractive for remote research experiments. And all these platforms use wheels for their locomotion and set different sensors appearing, including distance and light sensors. The Bucky robot is the successor. Bucky 2, designed for education and research, makes it easy to program and control robot behaviors, diverse sensors. Let's just go over these briefly. Word summary. There's quite a bit here.
What are you doing?
Rather than read all of these individual projects, I'm thinking maybe we just read a summary of all these different projects, because there's quite a bit, and I don't know if it pertains too much. It's just talking about really what they're built of, and I mean, we can. It's just if someone wants to pick up and read this section, I don't know how beneficial it would be to read this entire section, since it is just
Everything here is beneficial. It's not like something is less beneficial than the other thing.
okay.
Everything is.
Would you like to read this section then?
I mean, we could just read. I mean, we could just leave it for tomorrow or another day. We don't need to read the whole thing. It's already been 3 hours.
Yeah.
So
I was proposing maybe that we read a summary.
the summary wouldn't encapsulate anything valuable.
You don't think so?
No, it wouldn't. There's just too many projects, too many ideas. There's no value in reading a summary off of this. Everything here is just providing you like an insight into what failed, what succeeded, how it works. There's not much benefit for that. Now, I do understand that you're tired. So just like we can just pick up like tomorrow, tomorrow.
All right.
Post what section we left at in like the paper channel post, and
Sounds good.
yeah.
Yeah, I'll just add a note to my notes. All right.
What do you think?
It's a lot. Yeah, it's good stuff though. Definitely. What do you think?
Shit. There's a problem. Some guy says, I like to point out that the manage messages permission is granted for everyone in here, which means we can freely delete and pin each other's messages.
Oh yeah, Timmy was telling us about that earlier. In the feedback channel, he was telling us that users have the ability to ban and block any other users. Yeah, it's a huge problem. I didn't know if it was addressed or not. I guess I probably should look into that.
So settings, server settings. roles. Then we find, sheesh, man. So create private threads, touch files, some voice comment. They can't do this. This is for the creators. The creator has certain permission. Create public threads.
Interesting.
Yeah, so he's that guy there that was talking. He's a creator, so he might have certain things. So
Yeah, maybe so.
Pin the message. How do we solve this problem?
Higher permissions. On the low level, we'll have to dig into it.